Today, slightly out of the box with dishwasher simulation in PreonLab. We have not one, but two experts on the call straight out of the Plymouth, Michigan AVL office. And we'll just jump into today's agenda. So for everybody who is not familiar with AVL, a few words, and then we will jump straight into the topic with an introduction to PreonLab, a really innovative tool that we have here. And then I'll go into an application that is slightly non-automotive, but still very interesting. And yeah, I'm glad to have today on the show Antonio Ciarelli and Ryan Excel, straight out of the Michigan office. And I will, just after these few words, hand it over to the experts. So AVL, 75 years of experience in the mainly mobility industry, but as you can see today, we are also active in other areas. And basically everywhere where research is a topic, we are strongly involved. And as mentioned today, we are talking about PreonLab. It's an innovative, disruptive, meshless CFD tool. And it's very easy to use and also very nice to look at, as you will see today. And yeah, with that, I hand it straight to Antonio and Ryan. I will monitor the comments, so we have this live on LinkedIn and YouTube. Any questions we can try to address live or afterwards in the comments as well. With that, the stage is yours.
Thank you, Thomas, for that introduction. Hello, everyone. My name is Antonio Ciarelli, along with Ryan here. We are the main PreonLab support engineers in the Michigan location. And as he said, today we're going to be talking about, oh, my mouse is going crazy, sorry. We're going to be talking about how PreonLab can be used to model specifically dishwashers, but we can also utilize this for various other simulations. Oh, come on. There we go. So we're going to do a quick introduction and then we'll get into it. PreonLab is a SPH solver. So unlike your traditional CFD solving tools, it's not mesh-based. There's no need to spend hours to days meshing the area around it and the CAD itself. You use particle-based approaches to get a much faster simulation, both runtime and setup-wise. It has a very unique implicit formula instead of utilizing the traditional based. And as Thomas mentioned, it is very intuitive and easy to use, even if you're just picking it up from the beginning. It's definitely one of the tools easy to use and then take a longer time to master. But picking it up was coming from traditional safety background was very much a fun experience for myself when we started up. So the fundamental background, it uses Lagrangian instead of Eulerian equations. This is, as you can see on the screen below, this is because it allows it to move with the fluid, reduces the tracking needed for the mass and quantity, and it's a better way to set it up for the volume and tracking properties of the solver. The visualization here really gives a good view of how it is set up. Each particle interacts with each other within its own sphere of influence instead of having a fixed mesh point that all interact with each other, creating a more structured but takes a much longer time to simulate. Basically, is what happened there. So after that quick background, and if you have questions about how it functions, please add them to the chat. We will get to those. We have a video here showcasing the different ways we utilize this for a dishwasher. And to clarify any potential confusion, 52 and AVL work together with PreonLab. So we are AVL, but we work with 52 to utilize this software. And as you see here with that, you get particle and rendered views. You get some great imaging and videos out of this. So I'll let this finish one last time, and we'll start digging into it. So when they started doing the simulation, they wanted to figure out how to model it with dishes in it, capture the microfluidic behavior, and then also the forces, wetting, and temperature of each of the different parts inside of the dishwasher as the water hits it and cleans each of the individual dishes and components. You also have the ability to do rigid body dynamics, which allows you to see exactly how the arms of the dishwasher as fluid is being pushed through it would work and function realistically, instead of just only being limited to scripting the motion. This is just a nice video showcasing the similarities as it mimics the behavior. So here are some, as I was saying, some of the four main things that we were looking at. You have the cleaning efficiency and how well it's actually removing the soiling on the surfaces. You have some heat transfer as the thermal properties are able to be pulled out and inputted into the solver. Wetting and force analysis of each of the different components inside of the dishwasher. And then this all enables you to get a better analysis of how it can be placed inside the dishwasher, as well as how the dishwasher itself is set up for figuring out best placements to get the most efficient clean. With this specific simulation, we utilized 0.5 millimeter spacing with a physical time of 10 seconds for the simulation. And this took approximately 2 days to run on the solver on 32 CPUs. Now, this is not necessarily the most you could throw at simulation. We utilize MPIs and GPUs, which Ryan will get into at later in this presentation, to greatly increase the run speed and decrease the overall run time needed for each of these simulations. And you can see here the rendered view is a realistic view. We have different material settings and properties you can use to view and showcase what it would look like. But as you can see, the particles on the inside, that is the presentation to greatly increase itself, showcasing what is needed. One thing we can do is use multi-phase flow, so you're not limited to only water being put in. In this case, you can see somehow, I was not part of the team that got the properties, but they were able to get the properties of multiple different common kitchen and condiments putting on the plates. And all this can be done inside the same simulation. You don't need to run multiple. You can add multiple different solvers to the single simulation with multiple different properties for each one being customized. And this allows for Newtonian and non-Newtonian fluids to be run in this solver. Post-processing is where you get most of your interesting data and your fun images out of this presentation. And the main ones we were looking at here were the wetting time, which is a sensor you can connect to each of the solids. And this showcases how much time, either currently or overall throughout the run, that fluid was in contact and where with each of the solids. Then you can get current and maximum shear stresses and other forces on the solids themselves based on the fluid coming into contact. And my personal favorite is the path lines that you can actually generate to see where the fluid flow is occurring and really get a good idea of where the particles are moving as the simulation is going. And as I mentioned earlier, this post-processing, one of the main things they utilized for the dishwasher was to optimize the position and orientation of the nozzles to get the most wetting time and the most impact on each of these surfaces without drastically having to redesign the entirety of it. So any of you that obviously have used dishwasher, you usually got 2 to 3 sets of spinning blades that have water jets shooting up from them. And in this case, they were able to redesign the orientation of these jets to make sure you got maximum wetting for the basic setup that was already being inputted into this. Inputted into this design. Excuse me. One of the other features that we are able to do, and this utilizes a bit more of a setup, but it's still particle-based, is temperature and thermodynamic properties. So we have been utilizing conjugate heat transfers for a while now, but we have also recently, with the newest version, added convection and with heat flux and temperature boundary conditions. This allows you to set up custom, I'm going to play this video again if I can. There we go. This allows you to set up custom properties for each of the different solids for whatever you want to add in there. So you have the outer shell of the CAD, but then you also fill the CAD in with solid particles that you can set these properties for that allow you to get the temperature gradient that you would need to solve for based on the temperature of the fluid and then the steady temperature of the cup at the initial, and then utilizing those boundary conditions and heat transfer settings to get accurate results to see what would happen during this course of the simulation. And moving on from the dishwasher, we have a couple of further properties or further applications that we are looking into. One of them being a washing machine. There's really not too much to this one that we are concerned about with the actual washer itself. We're seeing, once again, the thermal properties are possible, but also the physical properties of where the water is flowing during the run. And you can see there's a little ball floating in the realistic one on the right. You can showcase the realism of it, and that allows you to see the full spread of the water throughout the run. This next one is something that Ryan here is actually able to develop these two views in the simulation, would be just a kitchen mixer. And this is something else we've been looking into with us playing trial and error to get the proper dough and batter settings to be realistic, but also, as you see on the right, the mixing settings to be able to mix in a secondary solid, or I'm sorry, fluid into this without needing an additional simulation. And on that note, I'm going to hand it over to Ryan here to take over for some of the key features that PreonLab has and has recently implemented.
Thanks, Antonio. So now, I'm going to run through some of the key features that really set PreonLab apart and make it such a great tool for your CFD simulations. One key feature in PreonLab that can help drastically improve your simulation times is CPS, or continuous particle size. With this feature, particles can take on any size within the user-defined range. This is accomplished all with a single solver that allows for particles to be coarsened or refined every step. This setup can really help keep performance results accurate while keeping simulation times as fast as possible. Here we have a video of a dip coat application that has utilized CPS to ensure quick simulation times. The continuous particle refinement here is controlled using a set proximity to the part's surface. And you can kind of see that here with this visualization. And then now we're looking at the particle sizes with each color. Recently added in version 6, the lateral adhesion feature helps model the complexities of contact angle hysteresis, which manifests as a force that acts against the flow of the droplet, impeding its motion and potentially bringing it to a halt. To capture this force in PreonLab, the lateral adhesion model comes into play by adjusting its parameters, specifically increasing the values. We can simulate a larger contact angle hysteresis, thereby generating a higher resistive force. Here we see how different droplet sizes deal with this lateral adhesion model over a few obstacles. Next, we have an example that shows the lateral adhesion feature in action as a window rain accumulation example. This video was entirely rendered in PreonLab. The Preon renderer is an extremely powerful tool for presentations and really visualizing your simulations. Another highlighted feature, which is shown off using our FCG gearbox benchmark, is the ability to simulate multi-phase, for example, oil and air together. And then also we see the continuous particle size again with the different colors. Our most recent release, PreonLab version 6.1, has added multi-GPU support, which allows for distribution of particles across up to 8 GPUs on a single node at once. multi-GPU simulations can lead to significantly faster speedups. And yeah, it does that by dynamically distributing the particles across the GPUs and then only exchanging them between GPUs when they need them to really get those increased simulation times. To benchmark these speedups, we'll show a simple breaking dam case with 88 million fluid particles and without considering post-processing. So showing the breaking dam test case, starting the first case was a 128 core machine with really good 43-hour runtimes, and then switching that to just one GPU, you get 2.9 times speed up using a simple A100 GPU. Then with multi-GPU supports, we also saw a 1.9 times speed up from 1 to 2 GPUs, and another 1.8 times speed up from 2 to 4 GPUs, reducing the sim time to under 5 hours, which is extremely impressive. If you're interested in learning more about PreonLab, please reach out to us at our support contact email or message either Antonio or myself on LinkedIn. We have several recorded webinars if you'd like to learn more about a specific application area like rainwater management in a vehicle tailgate opening simulation, virtual testing in vehicle water management, and virtual transmission design. We also have several quick tutorials on the 52 YouTube channel, including setting up materials for realistic rendering, as well as the surface proximity refinement for continuous particle size shown off here, and much more. That's all we have presentation-wise. Thank you so much for attending. Now we'll send it back to Thomas and open it up for any questions.
Yeah, thanks, Antonio and Ryan. Before we jump into the Q&A, basically just an outlook. And we have, last week we had battery topic. Today we had PreonLab. Next week, most likely, we will continue with scenario simulator and ADAS topic. You can rewatch this anytime, also here or on YouTube, and reach out with more questions. But yeah, coming back to the Q&A. So to kick it off, maybe I want not to mention not a question, but rather another comment. So if you're a student, you will have access for free to PreonLab. So any student at the university can join AVL's partnership program, and you can get access for free to this professional software. So just reach out to one of us or our webpage, and we can get it to you. As you can see, it's extremely easy to use, and maybe that's the first question to me. So typically, from a training perspective, how long would it take? Does it take your in your trainings to get somebody going?
Yeah, so I can take this one. We normally offer when we get a new customer trying to get a trial license, we do a 1-day specific training for whatever they're attempting to utilize, and I'd say 80% of the time that's enough to get them going for their span of the trial. But once we actually get a full scale license going and we're trying to do a full training, it's a 1 to 2 day multiple session training that we go over all the basics of the user interface, all the different solver settings, and the sensors that you'd be utilizing in your generic, as the tutorials show, simulations. And then we'll spend some more time once again specifically on a case-by-case basis of whatever the customer wants to utilize and actually run. And this allows us to really prioritize the situations they'll likely find themselves in when they're starting to use this. But by time a month or two goes by of customers utilizing this with or without our help and spending time with it, they'll be able to set up the majority of the simulations that they'll actually need. And then usually we only get called in for some major questions that they may not have run into yet or may not be fully covered by the tutorials, or some more advanced items that are needed for whatever simulation they're trying to run.
Perfect. And maybe a question to Ryan. What would you say is the most typical topic? I mean, today we had a rather, let's say, exotic topic for AVL. So how would you see the topic split still? Maybe you can elaborate a little bit on that.
Yeah, definitely. I see a lot of rainwater management cases. I mean, PreonLab's famous for its water weighting examples, very popular with vehicle soiling. But then on the gearbox side, single gear, planetary gear, lots of oil lubrication stuff. But yeah, it's great at those free surface flows. And yeah, very, very quick to learn.
Perfect. And which application would you say benefited so far the most from the multi-GPU support?
I'd say Gearbox was the start, and then with multi GPU, I mean, you're able to get smaller particle size and further. But yeah, the multi GPU is really aimed to take it from just the Gearbox, which was expected speedups with single GPU, to now the ability to take on a full car simulation. And yeah, seeing speedups typically 3 times than a normal server setup, which is extremely impressive.
Yeah, and when we come back to the dishwasher example, I mean, simulating a full loaded dishwasher in 2 days compared to building an actual real prototype, and having to test this and having to run this. Obviously, you can explore many more designs for a way cheaper cost than doing it on a real prototype, so to say.
And I'd like to add in on that as well that PreonLab doesn't, as you saw, it was only on 32 cores to run that. That was a single computer, 32 cores. So utilizing a server or GPUs obviously make it go faster, but you are able to run these on some more normal computers instead of what you will need for some of the heavier CFD softwares that would utilize a massive amount of CPUs to get any sort of reasonable runtime. This one is something that is very easy to set up on a standard, even work laptop to desktop, and then run with it depends what you're trying to do, obviously, but for a situation like this, a single computer was more than enough to run this within a couple days.
Yeah, and I think that is also, again, perfect for people who maybe are starting out with CFD or don't have access yet to the resources. Also great for PhD thesis and master thesis. Sorts of that kind of things. I think before we conclude, I think we also have to speak a little bit about the limitations of the approach. So I mean, no software is perfect, and there's certainly also things that we would recommend to do in our traditional tool FireM compared to PreonLab. Maybe can you elaborate a little bit on that? What you would see still on the classic CFD side?
Yeah, definitely. So one of the times that we're using Fire, before we're using PreonLab or FireM before we use PreonLab, will be for calculating the airflows for a vehicle soiling. So we start with the airflow in FireM, and then once we have that calculated, you can easily import that airflow into PreonLab and have a more accurate model where the airflow is already simulated, and then now you can simulate the water with that as well. So that'd be one of the main cases that I see where we're starting with FireM and then taking something into PreonLab there too.
And so kind of like the limitations you can overcome with combining some tools. Can you also maybe elaborate if there's more combination with other tools even that we could achieve?
Yeah, definitely. We're working on a model combining Mode Frontier and PreonLab for some quick optimization. But yeah, PreonLab is we have a Python console included, so very open to combining that with other softwares too. You can also import export in CSV and Insight Gold format, so it's very compatible with other simulation tools.
Yeah, so adding on to that, we have a few customers already that utilize, say, peer review or some other tools that they export data into if they might want something very specific that they're used to. Majority of our customers just utilize the renderer and to create and post-processing to get the data out of the scene that they need. But as Ryan said, you can export it as a CSV and do coordinate-based or frame-based to get whatever information you need out of this data or out of the simulation. And then on top of that, you also have able to, when, like you said, import via tensor fields to really make sure you get the exact airflow you need for any external flows that might be occurring to influence the system.
Also adding on to that, for something like a vehicle weighting case, you might want to export the pressures and forces from PreonLab and send that into another CAE tool to analyze kind of how your parts react to those forces. So that's also doable.
Perfect. Yeah, and I think the speed ups that you showed with the GPU, it opens a lot of doors for more optimization work, really like exploring different designs in a more systematical way, not so much trial and error, but really optimizing things. Yeah,
100% with that. You are able to, with the amount of time you save with PreonLab compared to standard, even if you're taking some other time needed to run, like Ryan said, run something with the stress forces to see how your parts react, you're still saving so much time up front with not having to mesh and take a week to make sure your simulation works before running it, that you can actually save more time on the back end to really make sure your designs are actually doing what you need them to. You're not running into a deadline, especially with prototypes, that you're going to have to push something out the door that you're not totally happy with.
Perfect. Yeah, I think this is a great concluding statement for today's session. Thank you so much, both of you, for taking the time today and showing us this kind of exotic use case, but still very interesting. And yeah, I hope to have you back soon with more topics, more nice videos. And yeah, thank you to the audience and have a great day, everybody. And see you hopefully next Wednesday again for another Lunch and Learn.
Yep, thank you for having us.
Bye. Thanks, guys. Bye-bye.
Thanks, everyone. Bye.